we looked at how OH can act as a nucleophile to a haloalkane. And we looked at how the Br can be replaced along the lines of this. In comes the OH, it attacks that positive carbon, the bromine leaves and you get ethanol where before you had bromoethane. We happy with that? Remember doing that? Remember writing the mechanism for it and so on? It turns out OH can do something else as well. Beforehand, this is a critical distinction. Pause please. Right. Beforehand, OH was acting as a nucleophile, but it can also act as a base. And if it acts as a base, it has a different mechanism. What it does here is it acts as a base and it takes a hydrogen. So, in comes the lone pair, attaches to that hydrogen. The electrons from the hydrogen go to the carbon-carbon there, and the bromine leaves. And what you get is an alkene. It can act as a nucleophile and do nucleophilic substitution or elimination. And it turns out that it's all about the conditions in which you have the OH. If you have, and I've gone back a page, aqueous, if it's in water, the OH behaves as a nucleophile, you get substitution and you get an alcohol. You happy with that? If it's dissolved in an alcohol, it behaves as a base and you get an elimination reaction and you get an alkene. Okay? And I want you to add to this alcohol here, hot. Okay? Hot ethanolic sodium hydroxide and you get an elimination reaction. Okay? If you have aqueous hydroxide, you get substitution reaction. If you have aqueous hydroxide, you get substitution reaction. If you have hot ethanolic hydroxide, you get an elimination reaction. And I think that's all I really wanted to talk about. You should be aware, of course, that hydrogen can be removed from either side. So if you remove that hydrogen, you get but1e. If you remove that hydrogen, you get but2e. Now, a lot of pupils get this mechanism horribly wrong. And what they try to do is they try to remove that hydrogen. If you remove that hydrogen and that chlorine, you get some horrible double carbocation thing that can't exist for very long. You've got to nick the chlorine and a neighbouring hydrogen. It can be that one, that one, that one, that one, or that one. It doesn't matter. Okay? And to do that, you need hot ethanolic sodium hydroxide. Okay. Haloalkanes, we've talked about polymers, and that's all I really want to say about haloalkanes. Quick reminder about the ozone layer though. Okay? CFCs get broken up, produce chlorine radicals, and the chlorine radicals then break up ozone. Back one. Here's the reaction for that. O3 plus Cl dot goes to ClO dot plus O2. That then reacts with O3. We did. We changed it. We went ClO dot plus O3 goes to 2O2 plus Cl dot. So just change it again here. ClO dot plus O3 goes to 2O2 plus Cl dot. Okay, so the chlorine radical is regenerated, okay, and goes on to destroy more ozone. Okay, pause there. Right, in this session we're going to be looking at the chemistry of alcohols. Some of it we've already covered in other bits, okay? Things like how to form an alcohol by nucleophilic substitution from a haloalkane we've already looked at. What we're going to be principally looking at is what are they used for, and critically, their oxidation reactions. Their oxidation reactions are absolutely classic AQA chemistry. Okay? Right. So, we're going to go through structures, naming, isomerism, physical properties, and so on. We know the definition of covalent bond is a pair of shared electrons. Recall the differences, recall the different types of physical bonding, as in hydrogen bonding, van der Waals, etc. Be able to balance simple equations, and we can do the rest of it. So, general formula: Cn H2n plus 1 OH. Okay? That's your alkane alcohol formula. We're not going to look particularly at aromatic chemistry. This is where you've got a ring of 6 carbons with delocalized electrons in the middle. This is called phenol. That would be called something else. It would either be methyl phenol or hydroxytoluene. But crucially, primary, secondary and tertiary structures. A primary alcohol is where the alcohol is joined onto a carbon that's joined onto one other carbon. Happy with that? Secondary is where it's joined onto a carbon with 2 other carbons attached to it. And tertiary is where it's joined onto a carbon with 3 other carbons attached to it. So, naming them: longest chain, remove the E, add ol, and so on. So this is 5-methyl hexan 2-ol. 1, 2, 3, 4, 5, 6, hence hex. Okay? It's 2-ol because the OH is on the second one, and it's 5-methyl. Though you could, in this case, have called this 2-methyl hexan 5-ol. And that would be equally correct because the numbers in total add up to the same. Butan 1-ol, butan 2-ol, 2-methyl propan 2-ol, and 2-methyl propan 1-ol. All isomers of each other. Critically, primary, secondary, tertiary, and this one is a primary. Not rocket science so far. You should know, and this is important, alcohols all do hydrogen bonding. Here, oxygen's got a lone pair, it's bonded to a hydrogen, and that lone pair is able to bond to the hydrogen on a neighbouring one. So all the alcohols have hydrogen bonding, and this makes their boiling points higher than similar molecules. Boiling points for straight chain isomerisms we're showing, again, well, here we've got 3 different isomers that are all the same, but the boiling points vary significantly. The butan 1-ol, you get the long chains, they line up well. Would you mind just closing that door for me? Long chains, they line up well. This chain lines up less well, hence its boiling point is less. And finally, this bottom one here is more of a globule, or a cluster, than a chain, and its boiling point is even less. Some pretty pictures of them, and moving swiftly on. They're pretty good solvents. This dissolve a lot of polar molecules, very much like water. Okay, because you can form hydrogen bonds and so on. Anything that can hydrogen bond is going to dissolve in an alcohol, no problem. They're also bases, and that's because you've got a lone pair here, and this hydrogen can be attached on. Okay, so they have basic properties. Not very good basic properties, but they do have some basic properties. Okay, you don't need to know this mechanism, but you do need to know it can be done. If you start off with an alcohol, you can make an alkene. What do we call the removal of water? Dehydration. This is the elimination of water, otherwise known as, also known as, dehydration. Happy with that? So you can dehydrate an alcohol to make an alkene, and previously we looked at how to make an alcohol from an alkene. Okay? Direct hydration. So you've got hydration, turning an alkene into an alcohol, and you've got dehydration, turning an alcohol into an alkene. Happy with that? Good. As I said, you don't need to know the mechanism, but it's there if you want it. Oxidation. Right. Hugely important. Examined ad nauseam. Primary alcohols are easily oxidized. Secondary alcohols are easily oxidized. Tertiary alcohols aren't. There are 4 definitions of oxidation. The addition of oxygen, the removal of hydrogen, increase in oxidation number, and loss of electrons are all definitions of oxidation. Are we happy with that? Here, you can remove hydrogen. You remove that hydrogen there. Here, you can remove that hydrogen there. There, no hydrogen to remove, can't be oxidized. Tertiary alcohols are not oxidized. Point number 1. Point number 2, ethanol isn't oxidized to ethanal. I'll come to the shape of that in a minute. The thing is, this carbon here, right, it's got the oxygen, but it's also got a hydrogen. If you can remove hydrogen, what can you do to it? If you can remove hydrogen, what can you do to it? Oxidize it. You can oxidize it to form carboxylic acid. Major point. I can't label this enough. A primary alcohol can be oxidized to an aldehyde, can be oxidized to a carboxylic acid. Okay? Ethanol, ethanal, ethanoic acid. Different types of bonding. Ethanol, hydrogen bonding. Melting point, 78 degrees. Ethanal, dipole-dipole attraction, 23 degrees. Pause, please. Ethanol, hydrogen bonding. Boiling point there. Ethanal, dipole-dipole only. Much lower boiling point. Ethanoic acid, hydrogen bonding, up to 118 degrees. It's got stronger hydrogen bonding than ethanol. Therefore, if we oxidize to this, to the aldehyde, okay, we've got an opportunity. If we want to collect the aldehyde, we need to get it out of the mixture quickly, because otherwise my oxidizing agent is just going to turn it into the acid. Okay? If I want the acid, all I've got to do is stick it in this case, a pear-shaped flask, and reflux it. Okay? Let's think about that for a minute. If I've got my mixture in here, and I'm heating it, alright? I'm heating a liquid, what's likely to happen to the liquid? It's going to boil. It boils, it goes up into here, it gets cooled down, and what happens to a gas when it gets cooled down? Condenses, and it drips back in again. Up, down, up, down, up, down. Okay? Boil, condense, boil, condense. Happy with that? That's called refluxing. And I make the carboxylic acid. Alternatively, if I want to make the aldehyde, I stick it in here, I start heating it. Remember, the aldehyde's got a much lower boiling point. So it's going to boil as soon as it's made. Boil it as soon as it's made, release it as a gas, condense it in here, and collect it as a liquid. There, okay, is my ethanal. Does that make sense? Okay? So, if we try doing the same thing with propan-2-ol, okay, we get propanone. Now, are you all happy with the structures of aldehydes and ketones? Do you know what they look like? No. Right, what I'm going to do in that case, so I'm just going to quickly draw them. Do I have a board pen? Yeah. Give me a blank piece of paper. Just pause it for a second. This is ethanal. What it is a carbon with a double bond oxygen at the end of a molecule. Okay? So if I add in the rest of the hydrogens, that is ethanal. Are you happy with that? And that is an aldehyde. And a primary alcohol gets oxidized to an aldehyde. Okay? Which you can then further oxidize to a carboxylic acid. And what that looks like is, that's a terrible diagram. that. Okay? There's my carboxylic acid. You happy with that? So an aldehyde gets oxidized to a carboxylic acid. All good? Whereas a secondary alcohol can't be oxidized to an aldehyde, so it's oxidized to a ketone. The most simple example of which is this one, propanone. Okay? A ketone is again this C double bond O, but it's in the middle of a molecule rather than at the end of the molecule. So to be clear, and you are genuinely expected to know this from memory, a primary alcohol is oxidized to an aldehyde, which is oxidized to a carboxylic acid. A secondary alcohol is oxidized to a ketone. Can I oxidize this any further? No, so it stays put. And a tertiary alcohol, not oxidized. Makes sense? Now, classic chemistry, you've got to know the difference between an aldehyde and a ketone, both what they look like and how to tell the difference between them. Right, moving on. The only equations you've got to write for this are using O in brackets. Okay? You're not expected to know any more complicated than that. You would do it with something like potassium dichromate. Potassium dichromate would oxidize an alcohol to an aldehyde or a ketone, depending on which one it is. So, here we have nice diagrams for it. Primary alcohol, oxidized aldehyde. Happy with that? Is this making sense now? Yay, nay? Which?
Meh.
Yeah. A secondary alcohol is oxidized to a ketone. Okay? And a tertiary alcohol not oxidized. So, there we go. There's my nice little not oxidized. Esterification of alcohols. Just hands up, how many of you haven't done this at GCSE? Esterification of alcohols. Right, you can put your hand down, you can put your hand down, and you can put your hand down. And you. And you.
I may have done it, but I don't remember it.
Pause, please. Esterification is where an alcohol reacts with a carboxylic acid. It's where an alcohol reacts with carboxylic acid. In this case, I've got methanol and ethanoic acid, and what I make is methyl ethanoate. Now, GCSE, I spent an entire lesson teaching this. We spend no more than 2 minutes teaching this now, because you're all bigger and older and you can get your head around it. Basically, the ethanoic acid loses the H. You happy with that? And the alcohol effectively loses the OH. In actual fact, it's the other way around. We're not going to worry too much about the mechanism. The alcohol loses the OH, and CH3 gets attached to that carbon there, and we end up with an ester. Okay? And you are expected to be able to draw the ester that you get given any carboxylic acid and any alcohol. Alcohol burns really well and can be used to dilute petrol. And it can be reacted with sodium to form things like sodium ethoxide, alcohols. That's not in the syllabus, you don't need to know about that. And this is just nucleophilic substitution, and we're not going to worry too much about that either. Infrared spectroscopy we're going to cover another day, but what I do want to make a point is, in infrared spectroscopy, the alcohols have a whacking great big peak, and should you ever be unfortunate enough to be breathalyzed, okay, an alcohol detector is actually an infrared spectrometer that is looking for the alcohol peak. You can prepare alcohols by fermentation, low energy process, renewable, and slow, produces impure ethanol. or you can do it via ethene, high temperature, catalyst, relies on fossil fuels, and I've overshot by 1, and so on. Uses of ethanol, alcoholic drinks, solvents, fuels. I'm not going to worry too much about that or that, and that's the end of that. Okay, thank you.